These slides will describe Graham's law of effusion. So we will define and explain effusion and diffusion, and we'll state Graham's law and use it to compute relevant gas properties. Gases are constantly in motion. They're in motion and they move so quickly that they often collide with one another and with the liquids and solids around them. There is a concept called a mean free path, which is the average distance that a molecule travels between collisions. This distance is determined by the speed of the gas and the number of particles in a given area. So if there are more particles, then more collisions happen. If the particles are in a smaller area, more collisions happen. See the presentation on kinetic molecular theory for more about this topic. So if we have two gases separated in a container that has a partition in the form of a stopcock, and we open the stopcock, the gases will move through the hole. The movement is entirely random. The particles will always end up completely mixed. This happens spontaneously whenever there is a mass gradient. So you have more of one particle on one side and more on the other. It's fast with gases, but it can be quite slow with liquids and solids. This phenomenon is called diffusion. So diffusion is the spontaneous process of molecules in a gradient spreading out via random motion until there's an equal concentration throughout. In this illustration, hydrogen and oxygen gases mix. We would see a reaction between these two gases at any temperature less than 1,279 degrees Celsius, but let's suppose that that is not what happens in this particular case. It's not the best example. As the gases mix, you can see that the hydrogen is going faster than the oxygen. So we have more hydrogen over here, and we have less oxygen over there.
I thought Leo was coming in to say hi to you.
Eventually, both gases are evenly distributed. Effusion is the movement of gases through a pinhole into a vacuum. Lighter gases effuse more quickly than heavier gases. In this illustration for effusion, which gas is lighter? We have an arrow indicating which direction we are effusing. It's the green one, because there are more green molecules than purple that have traveled through the pinhole. We can quantify this relationship between the rate of mixing and the molar mass of the molecules. Graham's law relates the rate of effusion to velocity. The rate of effusion is how much a gas can pass through a pinhole per unit time. Graham said that the rate of effusion is proportional to the root mean square velocity. In other words, the faster the gas is moving, the faster it will effuse, which seems pretty self-evident, but we never believe things as scientists until we have data to back it up. So Graham took the relationship between the root mean square velocity, and because the rate of effusion was proportional to the root mean square velocity, he could take a ratio between the rate of two different gases to describe the relationship between those gases. Okay, so we've got rate A over rate B equal to root mean square velocity A over root mean square velocity B. Then we're going to plug in the square root of 3RT over M. We're going to have an M sub A and a B, M sub B. When we do that, we end up canceling the 3RT. Because M sub B is in the denominator, it is negative, but the negative of a negative ends up being a positive. So that's how we end up with the square root of the molar mass of B over the square root of the molar mass of A. And I have simplified rate to just be R sub A here. Let's use this result to compare speeds of two different gases. What is the ratio of rates of effusion for hydrogen and hydrogen selenide gases under the same conditions? We use Graham's law of effusion to find the molar mass, and we find the molar masses from the periodic table. So when we do, and we plug things in, we find that hydrogen is 6.4 times faster than hydrogen selenide. Now, using this equation, we can also solve for how much time it will take to effuse if we are given a rate for one of the gases. We'll do examples like that in class. Now, this is an aside. The following is an interesting application of Graham's law. So our first nuclear bombs were enriched by using diffusion of UF6, or uranium hexafluoride gases. Now you may be saying, this is diffusion, not effusion, and you're correct, but it turns out Graham's law applies to both effusion and diffusion. So here we go. They put uranium hexafluoride through a porous membrane under pressure, and it would diffuse to a vacuum space, and the lighter U-235 would diffuse faster than the U-238, so they would slowly separate it over time. Now, the buildings used to enrich the uranium this way were about a mile long. We now use centrifuges, and this process happens much faster with much less waste, and it also uses a lot less energy. So, unrelated but interesting side note, the CIA actually disrupted centrifuges in Iran when they were using it to enrich uranium. They used malicious code. You can look it up. Kind of fun. Anyway, to summarize, mean-free path is the average distance a molecule travels between collisions. Diffusion is the spontaneous process of molecules in a gradient spreading out via random motion until they're in equal concentration throughout. Effusion is the movement of gas particles through a pinhole into a vacuum. The rate of effusion, R, is how much the gas can pass through the pinhole per unit time. Rate of effusion is proportional to root mean square velocity, and larger mass equals slower rate, because we get this ratio of rate A over rate B equal to the square root of the molar mass of B over the molar mass of A.